So going back to the notes, we're actually going to finish up the notes today. And we're going to talk about energy today. And one thing that we have to realize is that when we deal with energy, whether we're looking at a physical change, a chemical change, I don't care, any kind of change, energy is involved. Energy is doing something to the system. And one of the things that we have to also remember is that heat is not created or destroyed. So we're working with whatever energy we have available. Now, here's one thing I want you to do. This is a little experiment that I want you to do at your desk. I want you to grab the metal leg of your desk. Okay? Grab the metal leg if you can reach it, and there's some below your seat too. Grab it and hold it. And then tell me, does that feel cold or warm? Okay, now take your other hand and hold it up to the air. How does that feel? Warmer than the metal. What's the matter? Yours is warm? Was your leg against it or something? Okay. Well, Slush is the only one that has a warm leg. How's that? All right, now, the reality is, you can let go of those are actually at the same temperature. Okay? Those are both at the same temperature. Do you believe it? I mean, do they feel the same temperature? No. Here's the reason why. If you hold your hand up to the air, how many air particles are striking your hand versus how much you're holding on the leg? Who has more, the air or the leg? The leg. So here's what's happening. You're actually holding your hand up against something that always, quote unquote, feels warm to us whenever we're in the building. But when you grab that metal, you actually have more energy than the room itself or the leg on that desk. And so what's happening is the heat is transferring from you to a cooler object. Heat always transfers from high concentrations to lower. Now, this actually has some practical application for later on when you get with somebody else. Okay? Anytime you touch something and it feels warm, what is that other thing feeling? Cold. So when you touch something, you're like, whoa, that feels warm. And if it's a person, that person's going, whoa, that person's cold. Okay? So anytime you touch something and it feels cold in your hands, you're actually heating up that substance by losing energy. Whenever you touch something that feels warm, you're actually gaining that energy from that other thing until both of those temperatures are the same, or until you pull away from it. It's kind of like when we go to church. Oh my goodness, I wish they'd stop doing this. They always have a part where everybody gets up, shakes hands, and inevitably, the old women come running toward the young kids. Okay? Because when you grab some old person's hand, how does it feel? Cold. So they're looking for warmth. They're trying to suck the youth out of you. All right? Don't touch them. Don't give them your energy. All right? Remember that. The old people are trying to take your energy away from you. Also, another thing, if you're holding a nice newborn and it feels so warm, if that kid could talk, it'd probably punch you and curse you out, because if that baby feels warm, you feel cold to that baby. Same thing when you get with somebody later on in life and you're like, oh, you feel so warm. And that person's like, good God, you're so cold. So keep that in mind. In other words, unless you touch it and you're like, it doesn't feel so hot or doesn't feel so cold, now you're at the same temperature as the other thing. Okay? All right, just some tips to remember later on in life. I think I may have said all this. So again, heat always flows from warmer objects to colder objects. And technically the term cold isn't a term. Okay? Cold is what the ignorant say. Okay? You're no longer going to be ignorant after today. It's a lack of energy. Okay? It's not cold, it's a lack of energy. So when you walked outside this morning, you thought, whoa, I need my jacket because it's cold. What you really wanted to say, you walk outside, the presence of energy is lacking today. And you require cover. Very good. So answer me this. Does a coat make you warm? It contains the energy. Very nice. So if you leave a coat in the back of your car and you park your car outside and you get in the car and you're like, oh, there's my coat, and you put your coat on, it's cold, or it's lacking energy. So now you got to heat up that coat before it's actually going to keep you from losing more energy. So you got to warm that thing up. Same thing if you're lucky enough to be in the swimming pool and the fire alarm goes off. That's always a good time, especially in January where you get to run outside and you're only in your bathing suit. Yeah, and what's happening when you are feeling quote unquote cold? You're trying to heat the surroundings to the same temperature that you're at. Now, flip that over to summertime and you're on the football field, say at noon, okay, and that football field feels pretty warm. That football field's trying to heat you up to the same temperature as it. So, nice. Temperature, just as a reminder, is the average kinetic energy, so it's the average of all those particles moving around. We talked about that earlier. Biggie here, heat is never created or destroyed. It just simply moves around from spot to spot. Okay. Right now the sun's shining. It already had all that energy that was in there 5 billion years ago. Now it's just gracefully giving it to us. So the sun is losing energy while we're gaining that energy. I think we talked about joules earlier in the year. I can't remember when we did, but I think we did. Didn't we? I'm not just thinking of AP, I hope. Calorie, we all know what a calorie is, right? Those things that we eat or that we burn off. The reality is the food calories are 1,000 of these. Okay. In other words, when you go and get a Big Mac or something, it's 850 calories. Really, it's 850,000 calories, but they don't want to tell you that. Okay. That's why if you go to other places, they actually have on the label kilocalories, because that's what our calorie is. We're trying to make America feel good by not telling them that we're fat. Okay? But an actual calorie is the amount of energy to heat 1 cubic centimeter of water, 1 degree Celsius. Well, we're not going to worry about that. We're going to worry about joules in here. Have you ever heard the term endothermic and exothermic? Okay. Endothermic means what? Energy is absorbed or goes into the system. Exothermic means that energy is given away or exits. Yeah, good way to think about it. So here I have a nice, beautiful graphic that I created a few years ago. If my reactants start off with this amount of energy and it absorbs energy, then it's going to have more. Exothermic, flip it around. So it's kind of like a firecracker. You light that baby, boom, gives off all the energy. Now it doesn't have as much energy. Both endothermic and exothermic reactions require a minimum amount of energy for the reaction to begin, and it's called activation energy. I kind of like using this analogy. If I had a bowl of gasoline sitting on my desk here, and I start tossing matches at it, and a match goes in, what's going to happen? Good man. I could be chucking matches at it all day, but until one of them's lit, nothing's going to happen. But as soon as I have a lit match and I throw it in there, now we got something going on. We've got some activation energy. You're on it today. Yeah, man. Calorimeter. Ooh. This is how we're actually going to measure energy changes. We'll have a lab over it tomorrow. And it sounds really fancy. Calorimeter. It's a meter that measures calories. Coffee cups is what we're going to use tomorrow. And what it is, it's foam cups that doesn't allow for the escape of energy or the incorporation of energy if we don't want it. And so we'll do some calculations with that today. That's why I'm kind of speeding things up. But here are some factors that actually determine heat transfer. So the first thing is how well something can absorb energy and hang on to that energy. Some things are terrible at that. Like metals are awful. In other words, we can heat a metal up real fast, but then again, we can cool it down real fast. In other words, if you never cooked, fry some eggs, put it under a sink, water, you hear that steam, you can touch it now. However, water takes a long time to heat up, takes a long time to cool down. So if you heat water up and it's boiling, don't throw it on anybody. Good rule to live by. How much you actually have, the more of the substance you have requires more energy to heat that up. And the change in temperature. So if we're trying to change it by 100 degrees, we're going to need a lot more energy than if we're trying to change it by 3 degrees. So these 3 factors will be involved with our calculations, and I have an equation that's below here that will show that. Specific heat is actually a measure of a property that tells everybody how well this thing can hold energy. Metals are really bad, so they have a value of less than 1, typically, where water has a value of 4.18. So if you don't mind, I would like for you to highlight this. highlight that value right there. Just had it. Okay. Because if you highlight that, I will give that to you most of the time. But the thing is, on homework, I may not give it to you, but this never changes. We'll always use water for a lot of things here. Okay. On the test, I'll definitely give it to you. But in the homework, I might skip it on one of the questions. And then, obviously, the law of conservation of energy I talked about earlier today. We're not going to lose energy. We're not going to make energy. We're just shifting it around. And then, this is really important. The transfer of heat takes place between two objects until both of those objects are at the same temperature. And that's true when you have things that cannot generate their own heat or energy. Okay. And then this equation here is one that we're going to use today, tomorrow, in the lab and all that fun stuff. So this is our specific heat equation. I don't see the word specific heat anywhere, which is nice. Okay, we'll just, oh, there. We'll say that's our specific heat equation. Now, I want to identify some of these variables here. So Q actually represents energy or heat. Okay, so energy or heat, however you want to say that. And that's in the unit joule. Okay. M is our mass, and that's in the unit grams. Specific heat I'll come back to. Delta T, which is our change in temperature. And for this class, I just want you to get the difference. But an AP will actually follow this rule where delta T is equal to the final temperature minus the initial. I mean, you could do that, but if you get a negative, just drop it for this class. And the unit for this will be in degrees Celsius. And then C is our specific heat value, which is in joules over gram degrees Celsius, which is a really fun derived unit. Okay. There you go. And we'll do the practice problem, and then on the homework we have 2 practice problems that I want to work out as well. So we've got. So let's take a look at the first practice problem. What are we holding on to? All right. So looking at the first practice problem, it says calculate the quantity of heat in joules needed to warm water from 25 degrees Celsius to 95 degrees Celsius. And it says the cup holds 250 milliliters of water. All right. So let's write this down. So again, we're using this equation, and it's asking us to calculate the amount of heat. So actually, we're going to look for this. We're looking for Q. M, do we have the mass? Or do we know the mass? Is it given? Specific heat, which is in joules over gram degrees Celsius. I heard somebody say, okay. If I were to say we had 250 milliliters of water, how many grams is that? Does anybody know that conversion? Don't Google it. All right, if you don't know this, make sure that you know it today. And this is for water only. Okay? 1 milliliter of water equals 1 gram of water. Okay? And that's for water only, because water's our standard. That's what we use for doing all density things. So 1 milliliter of water equals 1 gram of water. So if we have 250 milliliters of water, what is our mass? Pretty nice. Okay, so let's go ahead and look at this. And let me ask you, since we're looking for Q and it's on the opposite side of the equal sign, do we need to rearrange these variables? No. It's already alone on its own side, so that's nice. So the mass is 250 grams. Specific heat for water is what? There you go, the 4.18. And I'm going to put the units like this, so joule over gram degrees Celsius. And change in temperature, we go from 25 to 95. So, and if you get a negative, drop it. What is it? 70? Yeah. So 70 degrees Celsius. And let's cancel out any units that can cancel. So degrees Celsius go away. Actually, let me scoot that up a little bit. So degrees Celsius cancel, grams cancel, and we're left with joule. So that equals something. Something, I hope. Like 73,150-ish. So 7.32 times 10 to the 4, and that's in joules. Again, 73,150 is what I got. Okay. Isn't that fun? Seem extremely difficult? It's not too bad. All right, let's look at another one. Everybody good there? So now what I want you to do is, in your notes, here, let me tap this guy first. Okay. Go to the specific heat worksheet, and I've got 2 more practice problems here that I want to work out. Okay. So everybody find that. And then I do have a video for the even questions for your homework tonight if you need them. All right. So practice problem number 1 on the homework. It says a certain metal has a specific heat value of 0.622 joule over gram degree Celsius. What is the mass of this metal if 7,422 joules of energy was used to warm the metal from 25 to 422? Okay. So here again, let's start off with what we know. Which variable are we looking for here? Mass. Very good. So if we're looking for M, we want to get rid of these guys by dividing them on both sides. So rearrange the variables before you start plugging numbers in. Do not cross multiply. Cross multiplying is the devil. You know that. Okay? So always show your variables rearranged before you plug them in. So now we have our mass is equal to Q over C delta T. Just clean it up a little. All right, so do we know our energy, which is Q? What is it? Q. So energy is always in joules. Yeah, so 7,422 joules. And Celeste, what is C? Good. So we got 0.622 joule. And again, I don't like showing multiple division signs, so I'm going to go grams degrees Celsius here. Okay. And the change in temperature, so 422 and 25, what is that, 397? Good. So what units can cancel out here? Degrees Celsius, joule, and what remains? Gram, which is mass. Okay, and whatever that equals. Anybody get like 30.1? I got 30.056. Fun? You ready for a challenge? Good. All right, let's take a look at the next one. And these are the types of calculations we're going to do with the lab. And these are super fun. It says a 147.3 gram sample of a metal at 103 degrees Celsius placed in a calorimeter containing 156 grams of water at 19 degrees Celsius. The temperature stopped changing at 24.4 degrees Celsius. What is the specific heat of this metal? Ooh. Let's draw a picture first. Okay. So tomorrow, what you're going to have is you'll have a beaker that's filled with some water, and it'll be heated. Some of you will have a Bunsen burner, some of you will have a hot plate. If you're lucky, you'll have a hot plate. And then we're going to have a calorimeter that's filled with some water. And I'll give you some random metals. Okay. And what we're going to do is we're going to place our metal, place this metal in our boiling pot of water. Boiling pot of water. Okay. And let me ask you a question. If something can't create its own heat, what will the temperature of that metal be? Whatever the temperature of the boiling water is. Good. And so if we said that the water in the container was at 103 degrees Celsius, what is the temperature of the metal? 103. Good. And then what's going to happen is, once this thing has been in there for about a minute or so, it'll be at 103 degrees Celsius. We're going to transfer it to our calorimeter, which initially was at 19 degrees Celsius. So we're going to take this and we're going to move it over into our calorimeter that we had our metal at 103. We place it in our calorimeter that has a water temperature of 19 degrees. What would you expect to have happen to the temperature in the calorimeter? Go up. Very good, because what's going to happen is, since the metal isn't able to generate its own heat, it's going to release heat until the water or its surroundings, the water, and it are at the same temperature, which it does until it gets to 24.4 degrees Celsius. Okay. So I think that's the picture that we want to look at. So here's a way to organize your thoughts. I would create a table. I highly recommend a table. And a table should look something like this, where you have your water for your calorimeter, and then your metal. Okay. You get your water for your calorimeter and your metal, and we want to do mass, our initial temperature, our final temperature, and C, which is our specific heat. Okay. We're going to put information in here, and again, this table is to help you to organize things. Again, you don't have to, but it'll definitely keep you from doing some dumb things here, which is always a goal. So let's write down some information that we know. So let's start with the water in the calorimeter. How much water do we have in the calorimeter? 156, good. So we have 156 grams of water. And what is the mass of our metal? 147.3. And again, there's a lot of information in that paragraph. So being able to organize your thoughts is really helpful. What's the initial temperature of the water in the calorimeter? 19 degrees, good. So the calorimeter is that thing that we're going to place the metal in. And what was the initial temperature of the metal? Carson? 103. There you go. Okay. So whatever the temperature of the boiling water is, and again, water can get over 100, and we haven't talked about it yet, if there's like stuff in it. And there's a lot of stuff in our tap water. Final temperature of the water in the calorimeter was 24.4. What was the final temperature of the metal? 24.4. This will always be the same, or should be the same, when we finish with our calorimeter. Okay, so we're going to place a hot object in the calorimeter. It'll heat up its surroundings, which will be the water, and then they'll both be at the same temperature when we stop. And then the specific heat for water is 4.18 joule per gram degree Celsius. We're actually looking for the specific heat of the metal. Okay. So once I know that, I mean, really, I don't have to go back to the question because all my things are organized. Now, I said that when we look at this, you're always going to have three of the four items, or three of the four variables given. We cannot start with the metal because technically we only have two of these. We have our delta T, our change in temperature, and we have our mass. We don't have the Q, We don't have the C because we're actually looking for the C. But do we have 3 of the variables for the water? Yeah. So we got our mass, we got our delta T here, and we have our specific heat. So what we want to do is we want to calculate the amount of energy that was absorbed by the calorimeter, because that'll be equal to the amount of heat that was lost or released from the metal. Okay. Go ahead. The 4.18? Yeah, that was in the notes. I'll always give that to you for water. Yeah. So it'll always be 4.18 for water, but for the metals, we're always going to calculate for that. Okay. So again, how much heat was lost by, or I'm sorry, absorbed by the water in the calorimeter? Go back and sorry. Ooh, that was lovely. The water in the calorimeter, that's how much energy was absorbed, and then the metal, how much heat was lost. Okay. All right. So knowing that, do we need to rearrange this equation for information for the calorimeter? No. We know our mass, we know our C, we know our delta T. Okay. So this is our absorbed calculation, so to speak. You don't have to write that, but just for clarification. So Q is equal to our mass, which is 156. Okay. 156. Yeah. Make it pretty. There we go. And our C, the 4.18. I'm going to put grams degrees Celsius on the bottom here. And our change in temperature, so 19 to 24.4, what is that? 5.4? Good. So 5.4 degrees Celsius. And that'll give me a number here. So let's see what that is. So I got 5.4 by taking the difference of 24.3 minus 19. And in that case, I got 3,543. And I don't want to shorten this one, because this is how much energy was absorbed by the calorimeter. So how much energy was lost by the metal? Good question. So if that's how much energy was absorbed by the calorimeter, how much energy was lost by the metal? What would you say, Elizabeth, if you were a betting woman? The same. Very good. So the amount of energy, or the Q that was absorbed, is equal to the Q that was lost, or released, if you want to say that. Okay, so our Q's are always going to be the same. That makes life so much easier for us. So knowing that information, we can now find out what our specific heat is for the metal. Now when doing that, make sure that we are using our equation. Expand that a little. Using our equation, but we're looking for C in this case, so we need to rearrange it. We're going to multiply or divide by the mass and change the temperature. So now it looks like this, where we have Q over M delta T is equal to our C. And we just found our Q of being 3,000, wherever it is. The 3,000, actually I'm just going to slide it over. This is our amount of energy that was absorbed by the calorimeter. Put you there. And the mass, what was the mass again for our metal? 147.3. And what is the change in temperature here? Ooh, this is fun. What is our change in temperature from 103 to 24.4? Yeah, 78.6. Good. What will our units be? Or who's going to cancel? Will any of them cancel? No. Which is a good thing, because that's what we want for our specific heat. And then whatever that equals. And hopefully it'll be a value less than 1. We'll say 6 is our Q value, or I'm sorry, our C value here. Say that again, I'm sorry. That's the difference in the two temperatures. So we went from 103 to 24.4. And hopefully your specific heat value is less than 1. Okay. For metals, I should say. All right, so any questions about that? Or what's going on there? Yes. For metals, it will be. Yeah, I can't think of a single metal that has a specific heat value that's greater than 1. Okay. Now, I'm sure that somebody probably could create one, but it hasn't been created yet. All right, so for tonight, I want you to work on the specific heat homework here. And let's see if we can identify when we'll just use this equation one time, or if we should make a table. Okay. So for number 1, is that going to require a table? No. What about number 2? No. Good. What about number 3? No. Now, also, whenever you see like kilojoules or kilograms, remember specific heat is in joule over gram degree Celsius. Make sure you convert those kilojoules into joules, or if you're given kilograms, get those to grams. Okay, so no. So none on the front side. Daggone it. What about number 4? Yeah, and here's your heads up. Placed in a calorimeter. That's a good indicator there. What about number 5? No, but there's kilo again. What about number 6? Somebody help Kate out. What's the conversion between kilo, let's say kilojoules and joules? How many joules in a kilojoule? 1,000. Kilo, 1,000. And don't go the other way. There's not. This is bad. That's bad. Okay. And here's so kilogram is equal to 1,000 gram. That's the easiest way that I remember. What's that? You got it. All right. Any other questions? No. Say it again. There you go. Now we're